Hello, everyone. Good afternoon. Thank you all for attending our talk. It's super fun to see so many people here. My name is Ahlam, and I have Z here with me to the left of me. And we both work as full-stack developers. And at our previous project, we actually worked together at Entur. And for those of you who are not that familiar with Entur, it's basically the organization that deals with everything that relates to public transportation data here in Norway, right? So we're talking like timetables, travel planning, ticket sales, ticket controls, and a lot more. All of this is based on Entur. So in a way, you can view Entur as the backbone of the Norwegian public transportation sector. And at Entur, our team worked quite a lot on something called offline-first architecture. And we've come to realize that it presents some pretty interesting challenges and pretty unique ones, and it has also introduced a lot of chaos into our lives, so we thought it would be kind of cool to hold a talk on this topic. Yeah.
So yeah, when I switched teams, I actually made this talk kind of as a summary of my time there. And just as a disclaimer before we start our talk, so first of all, this is an experience-based presentation, which means that we don't claim that we have the answer to anything, and instead would like to share the challenges that we've encountered along the way in implementing this architecture. And also, secondly, there have been many very skilled developers who have worked or are currently working on this project. So when we are saying we built something in this presentation, we're referring to everyone who has worked on this. All right, should we get started?
Yes. Very quickly, just an agenda. We'll first just start off by introducing the topic. So we're just going to introduce, very simply, offline-first architecture, and then we'll move on to the main principles, and then we'll finish off the whole talk with going through the challenges we've encountered as well as some of the solutions we've implemented.
Okay, so I'd like to start our talk with a little story. Story time. The year was 2020. It was a beautiful summer's day, and I was on my way to the office when suddenly I noticed that the ticket apps on my phone stopped working. I walked past one of those ticket machines by the stations, and I noticed that they also were not working. And I realized that, in fact, everything related to tickets were not working. Started stressing out a little, and slowly I decided to check the news. And that was when I found out that my job had landed on the headlines of the national news. And by the way, the original news was, of course, in Norwegian. We had to do a little editing with inspect page here on the browser to translate it to English, but you get the picture. Now, some of you who have worked in public transportation long enough might remember that fateful day when we stopped the entire country from purchasing tickets during rush hour. And for those of you who are Norwegian, it's like what Ahlam said earlier. Entur, it is the backbone of all of public transportation in Norway. So when it goes down, everything goes down. So this was really bad. But as the saying goes, every cloud has a silver lining, and this one was no exception. Because if you read all the way down, if you went into the news article and read all the way down to the end of the article, it actually says that just because everything was down didn't mean that we let the whole country travel for free. In fact, you could still buy tickets from the train conductors, the ones that are walking around on the trains, with their little ticket app on their phone after you have boarded the train. And let me quote the conductor who was interviewed. He says, "And then we'll try to sell tickets through our app, which sometimes works as well." Which sometimes work. So we decided to see this as a win that day in our team because we thought it's pretty cool that our app actually sometimes worked when absolutely nothing else worked. Went a little crazy with the animation. So what is this app, which only sometimes works when nothing else works? It is our lovely MT app. So MT is an abbreviation for mobile terminal, And it's the app used by people who work on the trains in all of Norway. So it's also used on some buses and some ferries, and it's written in native Android. So basically in Norway, if you board a train, there will be these conductors walking around and you can ask them to sell you a ticket. And most people use this as a backup solution. And sometimes the ticket controllers will also be checking your ticket by scanning with these apps. And I used to tell people that if you forgot to buy tickets on the trains and you get a fine, we're the ones that made the fines. So it's always fun to tell at parties.
Right. So this app that sometimes works when nothing else does is built on something called offline first architecture. But why is that? Like, why go through the hassle? Why bother when we could just sell tickets online, right? And there are mainly two reasons that we want to highlight. And the first one is related to the country we're in right now. Very quick, like, show of hands. How many of you have gone on a road trip in Norway? Like either by car, train, bus, anything? Quick show of hands. Yeah, everyone. Okay. Is there anything particular with the Norwegian landscape in comparison to, like, I don't know, Denmark or the Netherlands? Anybody want to give it a go? Exactly. Norway is an extremely mountainous country, and we have a ton of tunnels, right? And that is a very unfortunate situation to be in for a train conductor who's working on these trains and need to sell tickets, even though the trains are passing these tunnels and passing these mountains, right? Because they still need to be able to sell these tickets. So that's basically the premise of our app. We need to make sure that these train conductors are able to do their job. That's the main reason. But there's also a second reason, which simply is because MT has a strategic position in, as a backup solution in public transport. So in cases where everything goes wrong, like the fateful summer's day, we still need to be able to sell tickets. But there are plenty more advantages to this framework. And there's specifically one thing we want to highlight, and that is related to the digital divide. Because there was, despite a growing number of internet users, there was a report back in 2021, so it's kind of old, but still pretty relevant, that showed that 2.9 billion people, primarily living in developing countries, still don't have access to internet. And this is primarily due to, like, poor infrastructure, for example. And this is extremely concerning as more and more aspects of daily life occur online, right? So banking, for example, or grocery shopping. So we think that implementing an offline first solution can kind of help bridge this gap and ensure that more people stay connected and have access to essential services. Yeah. Okay, now we've been throwing around this term quite a lot, like offline first architecture, this and that, but we haven't really defined it yet. What does it really mean to be offline first? And I mean, a good definition is that offline first architecture assumes a lack of internet as the default. So in other words, you shouldn't really treat internet disruptions as an error condition, but you should rather see it as the status quo. So for us developers, that means you need to kind of change the shift. You have to change the way you approach software development. So instead of planning around a robust internet connection, you should rather develop your system based on an unreliable internet connection. That's what it means, essentially.
But how do you build a system based on offline first architecture? So to begin with, I'll explain the difference between offline first architecture and online first architecture, which is the more classic way of developing software today. So today, most apps are built with an online first architecture. In this architecture, you typically have a front end with a UI, and it reads data from the backend, and it writes data back to the backend. So you have a front end, you have a backend, and then they communicate with each other. And this is super simplified, of course. But then we have offline first apps. Now, before I talk more about it, I'd like to run a little thought experiment and ask a question. So my first question to you is, what do you usually do before losing Wi-Fi connection? Like, for example, before you board a flight, what do you tend to do? Anyone? Download. Yeah, that's a keyword, right? Now, I don't know about you, but I tend to download a bunch of things. I download series, music, podcasts. I basically do a lot of prep so that I don't get bored in the flight. So when developing an offline-first system, you're essentially doing the same thing. You download data temporarily while you still have internet access, and you prepare for when you don't. So this process is something we call caching, and it gives us the ability to do offline read. Okay. Now on to question number 2. So what do you do after you have already lost your internet access? So for example, during the flight, you have this urge to suddenly text a friend. What do you tend to do?
I mean, I'm kind of stubborn, and I know that I will probably eventually have internet again, so I just write out the text and just click send and hope it will be sent sometime soon, I guess.
Yeah, right? So that's like one way of approaching this. You can just try and send it. You can try to send the message either way and hope that it gets sent the moment we have signal again. Or maybe you can write it down somewhere on a post-it note and then remember to send it once you have landed. So what we're essentially doing here is that we're putting the message in a temporary queue, and the queue will then write to the external service once the system fulfills some condition, which in this case is getting the internet back. So now we're able to do offline writes using something called queuing. And if we combine everything together, we get what you call an offline-first architecture. So in an offline-first architecture, we have a front-end UI, and it communicates solely with a local database. So the local database acts as a single source of truth for all of the business logic inside the app. So everything the app does is based off the local data. And once we get our internet connection back, the local database will then communicate with the external server via caching and queuing. And this is a process that we call synchronization. And here we see a comparison between online-first and offline-first architecture. So this is probably the most fundamental thing we're going to be covering today. It gets a lot more complicated from here. If you don't remember anything from our talk, remember this slide. Okay. Let's continue. So now that we have some of the theory out of the way, I'll talk a little bit about the specific product that we have built, which is the app that we talked about. So I mentioned earlier that one of the main functionalities of our app was to sell tickets. So what we're essentially trying to build is a little shop, a little store, which must be available offline. So if you shop at a grocery store, you'll find a bunch of products on the shelves that you can put into your basket, and you can pay for it. So the things you're allowed to purchase from the shelves at Entur or in all of public transportation, they are called an offer. And to be able to sell tickets offline, the app, it kind of has to cache all of the offers. So we have a little offline read going on here. Yeah. And then we have the app itself. So here we have basically all of the functionalities of a cashier in the store. So here you check out the products, you take the payments, you print the receipt, etc., etc. And all of this has to happen offline. And once the purchase is done, we have to remember to inform the rest of the Entur organization that, hey, we actually sold a ticket even though we were off the grids. So this is done via writing data to Entur sales APIs. So here we have an offline write going on using queuing.
Yes, okay. So now we've got a nice little overview by Z over when offline first actually entails and how it works in theory, but what we haven't really covered yet is how it works technically, right? How does it work with code? So just to recap, we have this reading part, and we have a writing part, and a synchronization part. So if you, as you said, if you have to remember anything, remember that, at least. So I was thinking of going through the technical aspects step by step, starting with the reading part. So firstly, what you see on the screen right now is a very simple app architecture, like how data modeling is done. And app development. So building an offline first system starts in the data layer with the repositories themselves, as well as the data sources that the repositories delegate to. And the repositories in the data layer are responsible for combining combining the data sources to produce system data and then exposing it to the rest of the app. So if we zoom in a bit further into the data layer, we can see that an offline first repository requires a minimum of 2 data sources. So we have a local data source and then a network data source. So the local data source does not depend on network access to perform tasks whatsoever. And it is then the repository's responsibility to populate the local data source with the network data source. And with code, this is just pseudocode. It's not like amazing code. Don't nitpick at it, please. But we can use offers as an example, as the previously mentioned. So an example of an offer can, for example, be an adult ticket from Oslo to Bergen on the 24th of September 2024. And on the screen, you can see that the local offer, that represents the local data source. We have the network offer, which is the network data source. And the MT offer is the exposed data model. And in the repository, that's where all the fetching and the converting happens, right? Okay. So that is how offline reading is implemented. Or, I'm sorry, but how is offline reading implemented? And there are mainly, when it comes to caching, there are 2 particular things you need to kind of think about. The first one being how much to cache. And the other one is how often. So basically, when should you cache, right? And in an ideal world, you should fetch data from the external source whenever you have the opportunity. But when that opportunity arises is highly, highly context dependent, right? But for our specific case, using this MT device, we have chosen to cache right after the conductors have logged into the device. And the reasoning behind this is because we know for certain that the train conductors have internet connection, right? They're probably at home, or they're probably at like Oslo S, and the foundation for good internet is there, right? So we take advantage of this information and cache everything right there and then. But we also know for certain that the conductors have internet connection when they finish their shift, when they're settling accounts, and then when they log out for the day, right? And that is simply because such an action actually requires internet. So again, we take advantage of this and invalidate all the cache when the conductors finish their shift and logs out for the day. So that was reading. But what about writing? What about queuing? For offline writing, there are usually 3 strategies you can choose from, and which strategy you choose depends on the system's constraints as well as the type of data you're handling. But just a quick disclaimer before we move on. We'll only cover the strategy we used and we implemented, but if you're interested in diving even deeper on the different caching strategies, we have a lot of resources on the end of the presentation, but you could check out something called online only writes as well as queued writes. But we use neither of these. We use something called lazy writes strategy. Why is that? Well, data is a very critical part for both ticket sales, but also ticket inspections. So we need a strategy that can minimize the risk of data loss. And that is essentially achieved through lazy writes. So this approach involves writing to the local data source first, so you're updating the local data source, and then you're queuing the offline write so that it can notify the external services as soon as possible. And if there are any conflicts, you handle those, and then you update the local data source. And that is basically how lazy writes works, in theory. In practice, or on a technical level, how we've implemented it, we've done it through the use of something called service workers. And service workers are basically, you can view them as these little helpers. So you can just like imagine a bunch of small Oompa Loompas everywhere, right? Or carrying this cute little backpack. And when we perform an offline write, what happens is that we give these Oompa Loompas the data, which they just put in their backpacks, and then they're just waiting there, waiting until they realize that, oh, I have internet connection again, and then they push this data to the service, right? So that's how it works, essentially, and that is basically what is happening on the screen right here. And we also have a retry mechanism, if all fails. Okay, and now, synchronization and conflict management, or conflict resolution. Because when the network connection is restored again, the data from the local data source needs to be reconciled with the data from the external data source, right? And this requires a synchronization process. And there are two main ways to synchronize synchronize with the external service, and we can start with push-based first. Push-based synchronization means that it is the server that sends notification to the app whenever there's new data. And then the app basically just fetches the updated data. And you can view this, you can think of it like having a personal assistant in a way. So this personal assistant monitors your mailbox, and if there's any new mail, they basically come and give you the mail directly, right? You don't really have to do much. So that's how push-based works. While pull-based, on the other hand, is when the app fetches the data from the server as needed. So this happens usually when the user kind of navigates from to a new screen. And one way of viewing this is, we can take the mailbox example again. You don't have a personal assistant. You yourself have to go and check your mailbox every so often, right? And some apps also use a hybrid approach, which basically just combines both methods depending on the type of data you have. Right. Now, lastly, to conflict resolution. This could be a whole topic in of itself. Probably could talk for hours about this, but we'll quickly go through conflict management, because just to recap, if a system writes data locally when it's offline, but the data is not compatible whatsoever with the external service, a conflict arises, right? And this needs to be resolved before the synchronization part takes place. And there are many strategies to consider, but we've highlighted 4 specific ones. The first one, which is basically the simplest one, and that is basically just not caring whatsoever. Yeah, you assume that the conflicts don't really matter. It's not your circuits, it's not your monkeys, you don't care. You just assume that everything will work out anyways, and yeah, the users will probably fix the conflicts themselves. And this is also called last right wins, but conflicts don't matter kind of cling a little better, right? The second one is basically just, it involves basically tracking the changes with version numbers. Similar to Git, that's a very simple way of viewing it. We also have something called conflict-free replicated data type, which basically means that you design the data objects to be inherently conflict-free. And the last one is basically storing the operations and handling the aggregations on the server side. Very out of scope, plenty of references we'll show you later on.
Okay, so did all of this sound easy? That's a very rhetorical question. It's not. And remember, there's a reason why this app only sometimes works. So now let me talk a little bit about the challenges that we have met along the way of actually implementing this architecture in practice. And hopefully some of the solutions we have found. Okay, caching. First of all, did you guys know that caching things is really, really hard? It's actually one of the most difficult things in computer sciences, because it's one of those places where you encounter what you call the time-memory trade-off. because caching takes time and it takes memory, and there is no good answers as to how to balance it perfectly. And this is especially when we're talking about caching all of the train tickets in a train route in this country, because there's quite a lot of tickets you can sell in this country. Let me show you an example. So here we have a very classic train route. We have a train route from Oslo to Stavanger, I think. And as you can see, the train will go through 25 different stations on its way. And what this means is that we'll have to find every single combination of station pairs in this route. So we have Oslo to Lysaker, Oslo to Asker, and then we have Lysaker to Asker, Lysaker to Drammen, etc., etc. We have to find every single station pair. And I don't know how much grade school math you guys remember, but we have an exponential growth situation going on here. And for each pair of stations, there's also a bunch of different products that you could sell. So we have different passenger categories, we have different ticket types, or if someone introduces something called dynamic pricing, it also makes it more complex. And this is also a simplification. There's like a bunch more different things you can sell, different combinations. So what this all means is that caching everything takes a lot of time. And these offers objects that I keep talking about, they're not small objects, they are huge, they are very complex. We're talking many, many gigs of data. And just as a side note, the phones that we kept talking about, the apps, the phone, they have 30 gigs of storage space. So we have an optimization problem as well, right? So it took a lot of time to cache all of these offers. And when the team first gave this a try, I think the very worst cases took almost 20 minutes to finish caching. So you basically had to make an API request for every single station pair. And I think at some point we actually took down the offers API as well. And this conductor guy over here, he had to wake up in the morning, start caching train tickets before continuing his morning routine, like brushing his teeth. And I wish I was joking. I'm not. This is a real user story, user feedback we got. So, needless to say, this was not a perfect solution. But how did the team fix this? Well, this was done by creating our very own backend server, which is a form of backend for frontend. And it got the beautiful name offers cache. So I think this was done pretty much right after I started on the team, and at the time I didn't really realize what was going on, but I have since understood why. So what this server does is to, first of all, literally cache every single offer that could be sold on all of the trains in all of Norway. It just keeps caching every single night. It then processes and packages the data so that the app could fetch exactly what it needs with only one API request. The cache is then invalidated and overwritten with fixed time intervals. So for some routes, we cache once per night, and then we wait a little bit longer for others. And finally, it also compresses the offers objects. So we're basically trying to minimize the data in transit. And the cool thing is this solution actually reduced the caching time from 20 minutes at worst to under 1 minute in average. That's pretty cool. And I don't know if you guys see it, but we also have the additional benefit of this app becoming a lot more resilient. Because if the offers API, if that goes down, we still have some offers left that's cached in the offers cache. And if offers cache also goes down, we still have some offers left in our app. So either way, we will be able to sell something. We have like a double backup situation. Okay, so now we have cached everything we could sell, but then we still have challenges with the sales process itself. Do you guys remember that I compared our app to a little grocery store? Well, in normal stores, you usually have some rules for who is allowed to purchase what. So if you're at a pharmacy, you tend to need a prescription to be able to buy some medicines. If you're trying to buy alcohol, you might have to show an ID, right? Being offline, it's basically like being inside a shop where all of the employees have left the building and everything is up for grabs. So basically, we don't have any validation logic offline. So when you're purchasing a ticket at Entur, the purchase usually gets validated through this backend server, and the only job of this server is to stop you from purchasing things you're not actually allowed to purchase. Well, this server can't stop us on the app because we're offline and nobody can reach us. And so technically, we can run into situations where we have, for example, sold tickets that are no longer available. And this is kind of a problem. And how do we solve this problem? There's a pretty simple solution to this whole ticket validation problem. It's fast, it's reliable, it's robust, and it's especially great if you're under a lot of time pressure and everyone is telling you to just fix it. Does anyone know what I might be talking about? Okay, hear me out. So basically, you take all of the code with all of the validation logic or whatever your backend servers have to offer, and you hard code it directly into the app. Ta-da! And we're done, right? Why do we spend all that time worrying about caching and queuing when this just works on the day, and probably for that day only? Yeah. Unfortunately, as every good software developer, such as ourselves, know, hard coding things is gonna lead to a lot of problems down the line, because the moment anything changes in the backend server, our app is basically gonna stop working. But we still have to solve this problem. We still have to have some of these validation logic offline. So what do we do? That brings us to our second solution, which is libraries. So instead of hard coding and maintaining a bunch of business logic directly in our app, we go to the other teams and we force them to make libraries for us, which we then import. And it's super, super important that these libraries are maintained by the teams who own the business logic. So in this way, we don't have to keep track of every single change in the entire organization inside the team. So yeah, in our example, we have a sales library that's maintained by the sales team. We have a control library maintained by the control team, etc. And here again, we have the advantage of this app becoming even more resilient. I don't know if you guys noticed that. So if the Wi-Fi is gone, then we still have a bunch of business logic saved in the form of libraries in our app. And even if the libraries are not working, we might still have some hard-coded logic inside the app for the things that has to work. So, but then there's this one problem with the library solution, and it is resource allocation. So every time we ask these teams to make libraries for us, they tend to ask, why are we making libraries, an entire library, when you're the only ones using it? And this is honestly a good question. There's been many discussions about this, and there's not always a good answer. The answer can be, why are we the only ones using it? Maybe more people could be using it. Maybe more things could be more robust. But it is a good question. But let's move on. Okay. So now we have sold the tickets. The customer have their ticket, and they're happy. But this is still happening locally, offline, on the phone. And we still have to inform the rest of the organization that we've sold the ticket, because otherwise you have just taken a bunch of money illegally. So basically in this case, we have to inform the sales APIs that we've actually made a sale. And that should be fine as long as we get our internet back, right? It's not? So first of all, this nice little sales API that I keep on talking about is not just one API. We're talking about many more APIs. This is also simplification. We're talking about at least 10 or 20 different endpoints that you have to ping. So once you've sold a ticket, you have to register so much data for it to be considered a legal sale. You have to generate an order. You have to make sure the payments have gone through. You have to tell the accountants. There's a lot of things that you have to put into place for it to be considered legal. And one of the problems is that you have to register these data sequentially. So now we're having the problem with too many API calls again. And if one of the calls to one of these servers fail during the process, either because of lack of internet or because the APIs themselves are down, we end up losing a bunch of sales data. And that's when you get accused of tax fraud, which is something we want to avoid. So basically, we needed a right solution which limited the total number of API requests per sale, which makes us less vulnerable to data loss. And it has to persist everything that is sent in case something doesn't go through. And it has to have a mechanism that allows for retrying in case one of the many servers go down. And finally, it has to be easy to monitor centrally so that we get notified if something goes wrong. And that is how the team made yet another backend. And we call this one order import. We're really creative with names here. So this is literally a service that allows the rest of Entur to import everything we've already done offline. So basically, the moment the app sells a ticket, the sales information is stored, and this way we avoid data loss if one of the services go down in the middle of the process. And order import will then make all of the calls to all of the different APIs asynchronously using something called Kafka. How many of you guys have worked with Kafka here? Okay, some. Now, for those of you who aren't familiar with Kafka, it is a distributed data streaming service, but to get an intuition of it, just for this talk, you can think of it as a queue. It's not a queue, but you can think of it as a queue. Now, so what this solution does is that it limits the number of so what we essentially did here was to create a backend with internal Kafka queues that would handle all of these API calls. And this solution, it limits the number of network requests to only one per sale. So from the app to our internal backend service, as long as that one goes through, the rest is handled on the backend. And all of the sales information is stored as long as that one API call goes through. And since we have gathered all of the business logic in the backend server, it is much easier for us to implement and adjust the retry mechanisms. And finally, we also have the ability to monitor centrally. So instead of monitoring all of the different microservices and all of those different calls, we can monitor our Kafka topics instead. And again, we have a double backup here. I don't know if you can see it. So if we don't have internet or if order import is down, then we'll keep retrying on the app with our service workers, the little Oompa Loompas that Ahlam talked about earlier. And we'll wait there until the conditions are fulfilled, and then we can write to the order import again. And if something is wrong with the sales API, say that the sales APIs are down, then we'll be waiting at the order import, and we'll keep retrying, keep waiting with Kafka. So we have like a double backup. So either way, we'll keep retrying and keep waiting until the right conditions are met. We're just very, very persistent in this team. Okay, so now I've talked quite a bit about the challenges we have met on this journey of implementing an offline-first architecture, and I've talked about some of the solutions. So here you can see my little drawing of the entire architecture. So the blue parts, they are the external services. They're maintained by the external teams. And the purple parts are internal services maintained by our team. And as you can see, we basically have a double backup of everything you might need for purchasing a ticket. So in the middle, you have our app with the local database. and it caches from offers cache from the left, which then caches from the offers API. And on the right, we'll keep trying and retrying with a service worker to order import, and order import will be writing to the sales APIs. And then in the middle, we have all of our business logic that we store in the form of libraries. And this is essentially what it takes for a relatively complex app to sometimes work, when nothing else works. Okay, some final key takeaways.
Yeah, we've bombarded you with information. I'm assuming it was a bit of like an information overload, maybe a little bit. So we have a couple of takeaways we want to share, like some things that are important to remember. The first one being that offline first architecture naturally just increases the complexity of literally everything you build, like the whole system. So even the most mundane tasks, smallest bug fixes, most developments, it will take a lot longer to develop and to complete.
And there's a lot more risks involved, and we have learned some valuable lessons. So we have learned that caching takes time and memory, and there's a trade-off, and there's no good ways of balancing it. You risk duplicating all of your backend and your front end with hard code if you're under a lot of time pressure. And if you do that a lot, you might end up with mismatching business logic, and that creates conflicts. Yeah, it creates conflicts between different data sources. And you can also have a loss of data integrity, like in the cases where we can lose sales data.
Right, and one useful strategy that we found was to basically create a backend for front end for all the caching and the queuing. And this approach can actually, or at least for us, helped us quite a lot to scale the app and also just secure the app against downtime, for example, and yeah, assisting us with scaling.
Okay, and finally, before you decide to embark on this journey of implementing a offline first architecture, here's our advice. Ask yourself the question, do I really need this? And if the answer is yes, you can still ask more questions. You can go like, okay, does everything need to be offline? Do we need offline read and write, or is it enough with just offline read? Because it's possible to disable some of the functionalities in an offline mode in the UI side, right? You can make some of the buttons unclickable. That is okay. So yeah, just make sure to think properly through it before you decide to implement everything offline first. All right. Thanks for coming to our talk.